This question is asked by Vittorio, who wonders what will happen if a glass of water suddenly turns out to be half empty. A pessimist is likely closer to the truth about how everything will turn out than an optimist. When people say the glass is half empty, they usually mean a glass containing equal parts water and air. Traditionally, an optimist sees the glass as half full, while a pessimist sees it as half empty. Linguist Ketchen Molick notes that we choose which starting point to use in our perception. The size of the glass is a way to effectively show whether it is being filled or emptied. But what if the empty half of the glass turns out to be a vacuum? The vacuum will not last long, but what happens depends on the key question that usually goes unasked: which half is empty? In our scenario, we will present 3 half-empty glasses: a traditional glass with air and water, a glass with a vacuum on top, and a glass with a vacuum on the bottom. We assume that vacuums appear at a moment in time equal to 0. In the first microseconds, nothing happens. Even the air molecules are almost motionless. Air molecules move at speeds of several hundred meters per second, but at any given moment, some of them move faster than others. Several of the fastest move at speeds exceeding 1,000 meters per second. They are the first to enter the vacuum of the glass on the left. The vacuum on the right is surrounded by barriers, so air molecules cannot easily penetrate inside. Water, being a liquid, does not expand to fill a vacuum like air does. However, in a vacuum, it begins to boil slowly, releasing steam into the empty space. The water on the surface of the left glass also begins to boil, but the incoming air prevents this from happening fully. After a few hundred microseconds, the air rushes into the glass on the left, completely filling the vacuum and colliding with the surface of the water, creating pressure in the liquid. The walls of the glass bulge slightly but withstand the pressure and do not break. A shock wave passes through the water and returns to the air, adding to the already existing turbulence. The shock wave from the vacuum collapse spreads for about a millisecond through 2 other glasses, which also bend slightly as the wave passes through them. A few milliseconds later, the shock wave reaches the observer's ears, causing a loud explosion. Around this time, the glass on the right begins to noticeably rise into the air. The air pressure around the glass tries to compress the glass and the water together. This is easy to imagine using the example of a wine glass. The atmospheric pressure at sea level is about 15 pounds per square inch, and in a typical glass, the surface of the water and the walls of the glass vessel are under pressure of nearly 100 pounds from below. Usually this force counteracts the air pressure that lifts the glass from below. But in the glass on the right, the air pressure lifts it from below, while simultaneously pushing the water down. This is the force we perceive as suction. The vacuum on the left did not last long enough for the suction to noticeably lift the glass, but since air cannot penetrate the vacuum on the right, the glass and water begin to move closer together. By this moment, boiling water filled the vacuum with a small amount of steam, but the glass and water were moving too quickly for the accumulation of steam to matter. Less than 10 milliseconds after the countdown begins, they rapidly converge towards each other at several meters per second, with no air gap between them, only a few clouds of water vapor. Water strikes the bottom of the glass like a hammer, and since water is almost incompressible, the impact is a single, sharp shock. The force on the glass is immense, and it shatters. This water hammer effect is responsible for the sound sometimes heard in old plumbing when you turn off the faucet. He can also be observed in a famous party trick, where one claps the top of a glass bottle to break its bottom. In our case, the forces would be strong enough to shatter even the toughest glasses. An interesting fact, when I tried to calculate this, I bought some cheap glasses at the store and tested how much force it took to break the bottom. One of the glasses just wouldn't break, no matter what I did. I left it on my shelf and it doesn't match the other glasses, which annoys me a bit. Every time I look at it, I think, thank you, science. So I stick to the theory. The bottom drops down under the force of the water and hits the table, splashing water around and scattering droplets and shards of glass in different directions. Meanwhile, the top of the glass continues to rise. Half a second later, the observers, hearing a crack, begin to flinch. Their heads may involuntarily rise to follow the movement of the glass. The glass moves fast enough to hit the ceiling, shattering into fragments that then return to the table. The lesson is this: if an optimist says the glass is half full and a pessimist says it is half empty, then a physicist is simply shocked.